ঠিক আছে, তুমি ইন্ট্রোডাকশনটা তারপরে
তাহলে মিনিমাইজ করে দিন। So very good evening to all. I welcome Professor Nilanjan Mitra. Professor Nilanjan Mitra currently Associate Professor at IIT Kharagpur in the Department of Civil Engineering. He is currently a visiting Associate Research Professor at Hopkins Extreme Material Institute at Johns Hopkins University. His research area mainly on the computational material science, molecular simulations, fluid structure interaction, and mechanics of composites. Basically, he is involved in various. ঠিক আছে, আপনি ওই দিকটা স্যার আপনি মিউট করে দিন, তাহলে এই দিকটা হয়ে যাবে, তারপর আপনি
হ্যাঁ ঠিক আছে, মিউট করে দিচ্ছি এখন। ঠিক আছে।
So very good evening to all. I welcome Professor Nilanjan Mitra. Professor Nilanjan Mitra is Associate Professor at IIT Kharagpur in the Department of Civil Engineering. Presently, he is a visiting Associate Research Professor at Hopkins Extreme Material Institute at Johns Hopkins University. The Professor Nilanjan Mitra basically do research work on the computational material science, molecular simulations, fluid structure interactions, mechanics of composite. Basically, he is involved in various multidisciplinary research work. He guided various PhD, MTech students. He also guided, basically, he also have various postdoc fellow at IIT Kharagpur. He has published various internationally recognized journal and conference papers. He actively involved in research work. He is actively involved in various research project work. He has some research projects such as shockwave physics through a medium office at the Naval Research, and he also co-principal investigator of research that is development of smooth particle hydrodynamics (SPH) capability of naval application and Naval Research Board. So you can see that Professor Mitra is involved in various multidisciplinary research work. I also personally know for his research, know him for his multidisciplinary research work. I also worked for a few times with him. And today, Professor Mitra will give a talk on the material and the structure at the extremes. I welcome Professor Mitra to deliver his lecture here.
Thank you, Shubhajit. So can you all hear me?
Yes, sir.
Okay. So good afternoon to all of you. What I'll be talking about today is materials and structures at extremes. Now, this is what I should say is something like an offbeat topic in civil engineering. In civil engineering, when I started the civil engineering journey for roughly like 25 years back, I was told, or rather I understood, that civil engineering is all about like making buildings, bridges, and so on and so forth. But as we moved along, then what we understood is it is not only about like making some structures, but also the materials which are involved in there. And interestingly enough, like the materials which are, these materials are subject to different types of extreme conditions, maybe extreme loading conditions, maybe extreme weather conditions, and how to kind of design those kind of things is something which is important. Just to give you an example, for example, like if you are making a bridge structure somewhere near to Siachen, then the materials that you'll be using is not that very convenient or very easily available, right? I mean, these are actually not the same materials that you'll be using if you're making a bridge, let's say, somewhere in Kolkata. Similarly, if you think a little bit ahead, now, if you are designing any kind of like structures in the moon, for example, people are now saying that, okay, we want to inhabit the moon and so on and so forth, like inhabited moon as well as the Mars. Then in those cases, the materials that you'll be using for these type of making of structures are not the same like concrete and so on and so forth. You may be using some other materials. So it depends like where you're making the structure, and thereby materials plays a very important role. And what my research has been so far is basically working with materials at the extremes. And obviously the structure part comes along. Okay, by the way, Shubhajit was one of my, he worked, during his PhD, he worked with me in one of the projects. So I thank him for that. And I should also mention that all the works that has been done here has been done by all my students. So I'm just kind of taking the credit for all the works, all the hard works that they have done. But anyway, so let's get started. When we talk about extreme loading in materials, there are different types of loadings which we can have. Now, please understand what you mean by civil engineering is not like just only like any common structures that you see. It may be various intricate structures. For example, you can have something like a nuclear reactor, for example. These nuclear reactors are subjected to irradiation of materials. You have nuclear irradiation in those kind of materials. So when you have, those are, by the way, those light water reactors are of concrete materials, and these concrete materials are subjected to radiation from different types of sources. Now, obviously, you want to kind of put in a material or a coating in there such that it will not undergo radiation damage. So that is why, so that is an extreme loading for that of the material concerned. Now, if I were to kind of classify these extreme loading materials, there are different types of it, as I have shown in here. One of them is basically mechanical loads, which all of us more or less see and think about. That's basically, it can be a natural source, like let's say you can think of tsunami, earthquake, and so on and so forth. Or you can think about something like human-induced type of thing. Or you can think of something like human-induced type of things, like let's say particle, wave load, and so on and so forth. I mean, by particle and wave load, what I mean is it can be something like a bullet projectile or something like a blast loading type of on the material, and so on and so forth. Then apart from that, you can also have chemical attacks. For example, if you have a structure which is subjected to like strong acids, strong bases, then that can be something. You can also have chemical degradation. I mean, if you see any kind of like polymeric materials, I mean, in fact, polymeric materials are being utilized all over in the civil infrastructure. Now, these polymeric materials do undergo degradation over time. So we have to kind of understand as to how these polymeric materials will behave over time. So the chemical degradation plays a big role. Obviously, there is also another thing called irradiation of materials. In many cases, apart from the nuclear industry, you also have space radiations. Like, let's say, think about that, okay, I am traveling in a rocket, okay? So if you're traveling in a rocket and it goes, I mean, it leaves the Earth's atmosphere, then obviously you're subject to different types of radiations, especially UV radiations. How to kind of control for that? How to kind of make your material such that the UV rays will not penetrate the vehicle, or even if you're kind of like going outside in order to do some kind of repair, as you might have seen some astronauts do it. So how can you protect yourself against the UV radiations? So yes, it calls for materials. The next thing is your extreme environment exposure. So you can have, as I said, one of them is like UV. Other things can be like extreme hot and cold temperatures. For example, let's say the cloth that you'll be wearing in Kolkata will not be the same if you're working in Siachen Glacier. The temperatures are quite low. So that means you have to have some kind of materials such that it will prevent the extreme environment. I mean, nowadays people, I mean, there are some research which I'm aware of, which usually goes in the Scandinavian countries. What they do is that they think about like, okay, in the concrete material, they will put in some kind of material, which are called like phase change materials, by the way. So if you put in this phase change material, so even though the temperature outside may be something like -20, -40 degrees centigrade, inside temperature will not fall that much. So many advancements are coming on into the material part and which are incorporated within the structure such that it is beneficial to us. Okay. What I will go over here is that I will basically talk about all the different types of loadings that I've talked about. So I'll talk about different types of loading conditions as to what they are, how they can be mitigated, and most of my talk will be around the research that I have performed. Obviously, there are others who have performed on the same topic, but I will just focus on those which I have performed within this perspective of materials at extremes. Now, if you think about mechanical loading, there can be, as I said, two different types of mechanical type of loadings. One of them being natural, which is basically something like your earthquake type of loading. As you can see in here, this is an I-280 freeway in San Francisco following a Loma Prieta earthquake in 1989. Almost all the beam column joints and everything in the bridges, they were shattered. So that kind of raised the question, okay, the beam column joints might be the predominant weak points in the structure, and many research has been done in this regard. Many of you are aware of this cyclone Amphan. So it caused huge amount of damage, not only in Kolkata, but in places in Sundarban and others. So one of the main intent of a civil engineer, I think, should be to kind of protect these structures against such kind of natural damages. Now, how to do it? One of the ways is basically modify the material, make the material much more resistant, make the material much more resilient, such that you can develop these kind of things. Apart from natural, we also do have human induced. So given the activity of terrorists and many other situations, we are having this one as a new type of loading conditions, which happens in any kind of structures, and that is your human induced. One of those examples is something in 1995, Oklahoma City bombing. The entire building was kind of shattered to pieces just because one truck full of explosives were placed outside and detonated. So these things, I mean, even though they're not very common, but they do cause huge amount of casualties. And it's not only about the property, there are a lot of lives which are lost in this entire process. Now, if you think of a bomb or something like that, there is the one thing that you should understand. There is something called a shockwave loading. As you see in the picture on the right, you will see that as a bomb kind of explodes, it kind of like emits a shockwave, and that shockwave eventually kind of propagates and then moves any kind of material, even though it may be human, it can just drift them forward. So that's how a shockwave works. Apart from a shockwave, you also have something like a projectiles. So it may not be necessarily something like a ballistic impact, but sometimes what happens is in the bomb, you can place in some kind of like small particles. And when the bomb explodes, then these particles also can move at very high speeds, creating a projectile impact. And these projectiles can actually eventually break a structure. And not only break a structure, it can eventually cause loss of life. So those things are to be concerned, are obviously of concern for any person who is kind of designing the structures. And that's why, from a materialistic point of view, we should kind of do something with that material such that it can resist these kind of situations. To give you an example, as I said about like earthquake loading, this was long back during my PhD years. So what we developed is we developed something like a beam column joint element. This beam column joint element is something like what as you see in the picture on the right, as you've seen here, if you can see my cursor, you will see that this is a column, this is a beam, and this one is this beam column joint. Now this beam column joint, if you look into it, that's a complex structure, or rather a complex, I should call it as a macro element, in which it has like number of springs, number of shear panels, and so on and so forth. Each of these will be having some kind of material properties which are kind of given in here. They're like hysteretic properties, it is referred to as. Now, once it kind of undergoes something like a vibration along the top, which is basically simulation of your earthquake, then it will follow that particular curve of the material, and eventually it will give you a response which is down below. Down on the right hand side, you will see the response, and obviously it has been matched with that of the experimental response. So you see as to how a numerical model is kind of developed and then kind of validated with an experiment. And after this validation process, it is then put forward into any kind of existing softwares such that you can do or model like huge buildings and so on and so forth. By the way, this work is present. It is an open source type of code. So if anyone is interested, you can take a look at that. There is a website of this one by the name of OpenSeas, and this is primarily maintained by Berkeley. So I was associated with that when I developed a part of this code. But apart from this, there are many other things as well. Okay. Now, if you talk about, as I was talking about, like man-made type of hazard, the one of those hazard is basically, as I say, blast wave. Now, think about how to kind of develop a material such that it will not undergo degradation due to this blast wave. Now, for that, what we did is that, I mean, this is what we have taken up to IISc. IISc has a big facility for shock tube simulations. So what we did in there is that we took like different types of materials. We took like normal concrete type of materials. We took like concrete materials with some kind of like fiber reinforcements and various other types of modifications to it. Now, once we took those materials and then we subjected it to blast loading, the blast loading picture is something which you'll see on the top right-hand corner. You will see that there is a wave loading, and this wave loading, the maximum amplitude of that wave loading is something in the range of like 60 bars, which is quite significant. 1 bar is basically the 1 atmospheric pressure. Okay, so 60 bar, you imagine what type of pressure that we're talking about. So if you impose a 60 bar type of pressure to a small cylinder, I mean small cube, like a 100-millimeter cube, you understand as to what the impact it will be. So we took a normal type of concrete material, we took, like, as I said, modified type of concrete material, and then we were seeing as to what are the different types of degradations. And from there, what we can eventually suggest is that, okay, this material kind of performs better compared to that of the conventional concrete materials. Now, obviously, in here, when you're, I mean, if the material kind of like breaks completely apart, or it kind of like fragments and undergoes a granular type of flow, then you cannot do any kind of like evaluation of the material. So what we did is that we actually did some like microcity studies. Microcity studies means it is basically like a CT scan. So you must have, all of you, at least understand as to what a CT scan of a brain means. So similarly, what we can do is a CT scan of any kind of sample. But the difference in the CT scan of a brain and a CT scan of a sample is that the scans are made at like very small spatial resolutions. Whereas in the case of a brain, the distance are in the range of like millimeters. In this case, the distance are in the range of like nanometers. So once one picture, one slice of the picture and the other slice of the picture, the difference in between the two is something in the range of like nanometers. Anyway, with those things, what you can do is that you can find out as to what is the pore distribution, because concrete is actually a porous material. I mean, even though it's like a solid, it looks something like that, but even if you look inside it, you will see that it's a porous material. Now, how these pores are kind of evolving. As you see the pores evolve, by that you can make a justification as to when the concrete will kind of crack and when the concrete will completely degrade. So that is what we were doing with this entire process. Now, for case of projectile impact, you see in here as to how the things are done. Now, this is actually a picture from the institute where I'm in currently at Johns Hopkins. So what you see is that this is a big, it's called something like something in a combination of a shock tube and a gas gun. Okay. Why am I saying a complete combination of a shock tube and a gas gun? Because shock tube is something which just produces a shock. Gas gun is something which just has a projectile. In this case, it's a combination of both. The picture on the slide movie on the right, you see that there is a projectile which kind of enters a target, and as it enters a target, there are some kind of like waves which are getting generated. How the waves are getting generated, what are the fragments that are getting created out of it? So those things form a part of my research, and not only mine, there are many other persons in here who does this kind of researches around the world. So in a nutshell, what we are trying to do is that we are trying to break things in order to understand how to make it much more better. That's how I would say. Okay. Now, I think with this one, I hope you understood that, okay, we need to kind of really work with materials and such that you can modify the materials in order to improve its properties such that it is resistant to different types of conditions which are not, not in daily life. I mean, these are like extreme conditions. Okay, before we start on these things, typically I should say, yes, I do perform some kind of experiments, but primarily I'm a computational guy. So in the computational sector, we need to understand at a different level. I mean, it's not always just only one level, the quasi-static type of UTM machines you have seen. It's not like that. There are many other different types of things which you can probe. So let me go through this slide a little bit more. We need to understand about the story about a length and the time scale. Now, length and time scale means that if you see that there are different types of numerical simulations which are being performed in here. Now, what we do, or what I have shown you so far, is basically this part, the one in the blue, which is, so we say, is continuum theory. With the continuum theory, we talk about like finite elements and so on and so forth. With this, you kind of get a feeling of the material as to how the material or the structure will kind of behave. Sometimes we kind of go above that, or in a length scale which is like much more higher than that. For example, we talk about a macro scale model. Now, macro scale models, the example of that is something like a beam column joint which I provided. Think about, we are talking about a, let's say, a 3-meter column, or a, I don't know, a 2-meter beam. So those things are being modeled like with only one element. So obviously that cannot be done at using your finite element, because finite element, it cannot take like 1 meter type of specimens. So those things are typically done at a macro scale level. So that means the example which I gave you for the beam column joint, that is an example for a macro scale model. Below that comes the continuum scale, or the continuum scale in which you actually discretize the entire thing with like finite elements or mesh free methods or whatever, those kind of things. But continuum scale is also not appropriate for many different applications. Think about like, okay, there is a crack in the material, for example. Now, can you really tell me that how many crack fragments will occur, or rather crack directions will happen? So that cannot be done with the continuum theory. So you have to talk about a scale which is like lower than that. And this lower than that scale is something which is a mesoscale. So we talk about like dislocations in the material, like if it's a metallic type of material, then there are dislocations. If it is a ceramic, if it is a polymer type of material, then there is something called a crazing, and so on and so forth. Below that comes the molecular level. So at the molecular level, you see as to what are the molecular interactions, how these molecules kind of eventually play a role, and so on and so forth. So remember, in a continuum theory, you typically require something like a material law. But this material law is not required when you're doing something like a molecular simulation. All what you have to do is to kind of think about as to how the molecules will interact with each other. And that, in a combined way, kind of defines your constitutive law for the material in the continuum theory. Now, there are some things which a continuum theory cannot do. So that is why you require these kind of things. For example, like if I'm think about like, okay, I will take a ice, just an ice block, and you're applying some kind of load to the ice block, and the ice block kind of changes to that of water. So effectively, what is happening in here, this is a very standard process, right? Everyone has seen ice, I believe. And if you're applying load to that of the ice, you will see eventually kind of like, undergoes a phase transformation to that of the water. Now, if you think of it in one way, this process of phase transformation from that of the solid to that of the liquid, that is something which cannot be modeled with your continuum theory. You have to work with the molecular level. So in those type of situations, we are interested in doing molecular simulation. In fact, for example, when you're talking about like impact loading, or like projectile impact, or even like a blast wave type of impact, those situations, what happens, the material can eventually vaporizes, or material eventually melts. So in those situations, continuum theory may not be the right approach. So it depends, like what type of situation that you're dealing with, what type of materials you're dealing with. Depending upon that, you basically choose your simulation methodology. Now, below the molecular simulation comes something which is called electronic contributions. Now, molecular simulations we are basically dealing with like ions. It does not really take into account the charge or the electronic contribution. Many times, we do require that electronic contribution. Think about like a standard chemical reaction, for example. Any kind of chemical reaction that happens, there is a interesting thing about like formation of bonds, right? You all know that, okay, at least you have read in your class 11 or 12 in those standards that there are different types of bonds available, right? Covalent bonds, ionic bonds, and so on, a lot of different bonds. Now, at those situations when the new bonds are getting formed, now that is what molecular simulation cannot do, because molecular simulation is still within the realm of your Newton's laws. You actually have to kind of cross that limit from the Newton laws to something like Schrodinger's theorem in order to come to this electronic contribution, in order to see as to how the bonds are getting formed. So that calls for something which is a electronic contribution. Now, I've talked about different ways or different steps of simulations that can be performed. Now, remember, all these different scales of simulations require a different type of length as well as the time scale. If I'm looking into a macro scale type of things, we are talking something in the range of like seconds, at least seconds or more than that, seconds, minutes, hours, and so on and so forth. And if I'm looking into the spatial resolution, we're talking something in the range of like meters or so. Okay. Now, if you talk about or continuum theory, macro scale, they're all of the same nearly. But if you're talking something in the range of like electronic contribution, then the time scale that you're talking about is something in the range of like femtoseconds. Okay, 10 to the power minus 15. In the range of like your spatial scale, you're talking something in the range of like angstroms. So that's like way smaller at way smaller level compared to what you really see. Okay. Now, this length and the time scales, if you think about from the experimental perspective, obviously the way that I think is that any simulation is good, provided you really see the thing as to what is really happening. So you can do a lot of simulations, but unless and until you kind of compare that to the experimental results, it really does not have any kind of meaning as such, at least to me. So when you're kind of probing these different types of experiments, you see that there are different types of machines which are available. This is something which you have already seen, the servo-hydraulic machines. The servo-hydraulic machines are nothing but your UT machines or universal testing machines. I think almost everyone has seen them in their labs. Now, apart from that, there are also other types of machines. Okay. Now, these UT machines can only probe up to a strain rate of something in the range of like 10 to the power 0 per second. But if you talk about some other types of machines called the Kolsky bar machines, those can take your strain rates way beyond 10 to the power 0. So we can probe something like a 10 to the power 4, even 10 to the power 6. If you want to go something in the range of like 10 to the power 6 per second, so that's a very fast loading. Okay. So in those situations, we talk about something like a laser shock. So as you see, all of these machines that I've mentioned in the top slide, I mean, like experimental investigations possible, all of these machines are out there. People do experiments with these, and with those experiments, they kind of match it with what they obtain in your simulation. So remember, like if you're doing something like a molecular simulation, electronic contribution, we are generally talking about something in the range of like laser shock, or at least in the range of like pressure shear plate impact. Okay. So those are the situations that we're talking about. But if you're doing something like UTM type of simulation or UTM type of things, then we are talking in the range of like either continuum theory or macro scale type of theories. Okay, so this is just to give you a brief background about what the different length and the time scale means, and what are the different types of experimental investigations that are possible in those situations, in those different temporal scales. Now, let me give you a brief about some research directions. I mean, people do work on that. I will show a brief about it. I understand that the slide is like too much. So the way I have done it is basically I've kind of like colored it in different ways. You see at the extreme right-hand side, you see something like a blue color. The molecule that you see in there is called polyvinyl chloride, PVC. PVC material, I think almost every one of you have seen. Any pipe material that you're seeing, that's a PVC. Okay, almost any pipes. And apart from that, there are many other applications of PVC. Now, what we were doing with that is that, okay, now this molecule, if you see, if you subject it to some kind of like shock loading, then obviously the molecule will degrade after some time, right? So we were trying to find out as to the point as to where this molecule will degrade. Eventually, it does degrade. And I mean, how does it degrade? Is it the carbon chains which kind of breaks? Is it the chlorine chains, the methine chlorine chains which breaks, or the methine chlorine which breaks? So that is what we are trying to figure out. Now we can say, okay, I mean, how does it really matter? Yes, it does matter. Because if you can understand as to which of the parts will kind of degrade first, you can reinforce that part. If you can reinforce that part, that means you can make a better material which is based upon PVC, but a slight modification of the PVC, such that when you apply a certain amount of shock loading, the molecule will not undergo a degradation. So that is what is important. Next, if you come into something like the yellow part, which is actually on the center top, I should say, you see, it is something written to be as isotactic, what this molecule that you're seeing is something called a polypropylene molecule. Now, this polypropylene molecule can exist in different formats. It can exist as isotactic, syndiotactic, and so on and so forth. Now, you might be thinking, what is tacticity? Tacticity of a material is where your methyl groups are placed. So if you look into a molecule, you have a carbon chain, and you have the CH3 molecules placed for the case of for the case of your polypropylene. So CH3 molecules can be placed alternatively, like in alternately on the right and the left hand side, or you can place like all of them on one side, like all of them on the right side, let's say, or all of them on the left side. So depending upon that, you think about something called tacticity in the molecule. Now, what we were doing in this case is basically we were taking that isotactic polypropylene molecule, and then we are just stretching it. As you are stretching it, this polymer undergoes a very interesting type of phenomenon. It undergoes something like a crystal structure. It is actually a crystal structure, and it undergoes to be something like that of an amorphous type of structure. So now let me point out something in here, because as I understand that almost all of you are from civil engineering background. When I talk about a crystalline type of polymer, it is not like crystalline type of shape that you see in any kind of other crystal, like let's say, for example, sodium chloride or like a normal table salt. It's not a crystal like that. What this one means for the case of a polymer is that it will have a definitive helical structure. Almost all the polymers will have a definitive helical structure in order to classify them to be as crystalline. By the way, one of the interesting polymers that almost all of us has is your DNA and RNA. So you must have seen a structure of a DNA RNA. It's like a helical type of ring, right? So that helicity is actually what determines the crystallinity of your polymer. Anyway, so when you have this, it is usually in a helical format. Now, when you have this helical format and then you kind of stretch it, at what particular point of time it loses its helicity. So where it loses helicity, that is what we were determining through this entire process. Yes, obviously we have done some kind of like molecular simulations in order to get to that, but that's what it is. Okay, now let's come down to the part below. You see that one part is highlighted in red. Okay, there is something like which says EPON 862, and then there is something called a DETDA hardener. What this one is meaning is basically it is normal epoxy resin. You use epoxy resin for almost everything. Think about like you're making something for the cars to some projects at your home. You're using epoxy resin for any kind of adhesive type of materials. That's a very common adhesive material. Now the question is, does this epoxy resin, when you subject it to different types of loading conditions, like let's say uniaxial loading condition, for example, like uniaxial stress strain, or you subject it to something like a triaxial stress strain, are the responses the same? Well, what we figured out, not really. The triaxial response may be something like which is completely brittle in nature, but if you think about an uniaxial type of response, it is completely, ductile in nature. So that's interesting. So that means usually if you look any kind of like adhesive manufacturers, so what they say is that, okay, it has this much amount of peel strength. So they are not actually providing you the exact picture. The peel strength is something like, okay, when you're just peeling it off, that means you're pulling something like a uniaxial type of loading situation. So that is the value that they're giving you. But the material does fail in many different situations at a triaxial type of situation. And in triaxial, the behavior of the material is entirely different from what we have for the uniaxial case. So just looking at the peel strength may not be the right thing to do when you're thinking about like any kind of adhesive materials. Okay, the one on the right hand side of the slide, which is colored somewhat in your white colored, or which is not at all colored, I should say. This is again something looking into your polypropylene molecule. As I was talking about, by the way, polypropylene, I think everyone is familiar with that. If you're not familiar, it is basically, it's found in almost all the cloths that you're wearing. If you look into the cloth, you will see that there is some percentage of polypropylene in that cloth. So polypropylene is a very common molecule which you see around. So this polypropylene molecule, as I was saying earlier, that it has different types of tacticity. So you can see, as I've shown two pictures in here, one of them is like isotactic, Another of them is syndiotactic. Syndiotactic means it does not have any proper helicity, or it is something like an amorphous type of material, whereas isotactic means something it is like crystalline and it has definitive helicity. Now, what we were doing in here is that how to kind of identify that whether the material that you have or your polypropylene molecule that you have, it is like isotactic or it has like syndiotactic and so on and so forth. So what we were doing in here is that we were doing spectroscopy. Spectroscopy is something which actually any chemistry people will do. I mean, almost always. What spectroscopy does is that it kind of probes at what are the different types of vibrations that are present within the molecule. So in the case of your polypropylene, it has, let's say, CC bond, CH bond, and so on and so forth. So as you see the peaks that are in here, like one strong peak or some of the other peaks, you will see that each of the peaks correspond to something, some of the vibrations that are present within the molecule. Now, when I say vibrations, now obviously you might be thinking that, okay, you know what, even though the material like isotactic or syndiotactic, it will have the same, molecule as such. It is oriented a little bit differently, but at the end of the day, it is the same molecule. Yes, it is. But the thing is, the way it is arranged, there is also something known as molecular vibration rather than just the specific bond vibration. Now, if you want to probe the bond vibration, then what you do is something called infrared spectroscopy or Raman spectroscopy. So that's what you do in order to probe the vibration of one specific bond. But when you talk about something like the molecular vibration, what you do is something called terahertz spectroscopy. Different ranges, different frequency ranges that we are probing. So you can basically see the entire molecular vibration of that molecule. And that is what we are doing in here. And we were showing that, okay, using this terahertz spectroscopy, you can really identify the differences in between how much amount of isotacticity the material has compared to that of the syndiotactic, what are the different types of defects it can have, and so on and so forth. Okay, so this is all what we have for, let's say, polymers, polymeric materials. Polymeric materials are something like chain molecules, as you have seen in here. Almost all the molecules are like chain molecules. And these chain molecules have very interesting characteristics because it is lightweight and it can be pretty strong. Like, for example, if you think about nylon, for example, it's pretty strong. Kevlar material, it is pretty strong. Even in comparison to that of the steel, for example. So polymeric materials have a great role or great application for case of research as well as for normal applications. Now, when you think about, like, apart from polymers, if you think about something called minerals, okay. Now, almost all of you, as I understand, are from civil engineering background, so you must be knowing about, like, okay, different types of minerals. For example, being your cement constituents. As you know, when you have the cement, it has like different types of constituents in it, like, let's say, C3A, tricalcium aluminate, C3S, tricalcium silicate, and so on and so forth, right? Also gypsum, and there are many of them. Now, all of these are basically minerals. And as a matter of fact, all of these minerals are naturally available. At some places, you will find those minerals. And these minerals have very interesting characteristics. As you can see in here, the same as that of the previous slide, what I did is that I kind of broke up this slide into 3 different parts. You will see one part at the left-hand side, which is colored as yellow. So that material, what you're seeing in here, is called tricalcium aluminate, C3A, one important constituent for that of your cement particles. Now, this C3A, that is what you're looking into at the top part, is how the molecular structure of the C3A is arranged. Yes, anyone has a question in here? I think I heard something.
So there is one comment that you have to asking the height that sharing bar it is showing in your screen.
I have to do what?
The height.
Repeat again, please.
In your screen, yeah.
Okay. So can you see now?
I just click the
height. I think so.
Yeah, now it's fine. And is there any question? No. Yeah. So please you continue.
Okay. So as you can see in here, you have a tricalcium aluminate, which is on your left-hand side. So that tricalcium molecule has like different things in there. Like, the colors of them will indicate, like, let's say if you have your red color, then that corresponds to an oxygen molecule. Your pink color corresponds to aluminum. And then you have the green ones, which are basically your calcium. Now, if you have this tricalcium aluminate, you can do a lot of different things with that. I mean, what we were doing in here is that we were taking the tricalcium aluminate molecule and then subjecting different types of loading conditions, like let's say uniaxial loading, triaxial loading, uniaxial compression, triaxial compression, shear, and a lot of different things we have done with that. So we were observing as to how does this, you see that, I mean, this circular structure, how that circular structure is kind of like changing, okay? How the structural structure is changing. And as that structure is changing, you're getting differences in the behavior. So remember, tricalcium aluminate is not only the only material which is available in cement, it is also utilized in many different things. Many of you might be having dental problems, for example. Now, if you go to a dentist, sometimes they take out your teeth and they put in something else, some other materials in there. You remember, I mean, if you look carefully into it, it is, most of them is basically tricalcium aluminate. So a tricalcium aluminate is not only utilized for cement industry, but also for your dental applications as well. You require that to kind of like, I mean, fill in your, let's say, tooth. So we were studying about this tricalcium aluminate as to how it performs and so on and so forth. The next that you see in here is basically, next is basically I will be discussing about the one at the top part, which is colored in blue. You will see this one is something called gypsum. Okay, gypsum is very common material, and it is used as a wide, I mean, different types of applications it has. I mean, if you're doing some kind of like painting and other things, obviously you must have learned about like gypsum, plaster of Paris, and all those kind of things. So these are basically those type of materials. Now, if you look into this plaster of Paris or gypsum, these type of materials, it has very intricate structure. It means it has like a layered structure. So gypsum is basically calcium sulfate. Okay. So calcium sulfate has a layered structure, and then in between that, you have something like your water molecules. So now, when you're applying some kind of like loading to that molecule, obviously, it will undergo something like a slip. It will undergo something like a some other kind of behavior. So that is what we were seeing in here. Like, okay, if you, I mean, as you know, the gypsum, if you kind of heat it to something like 350 degrees centigrade, eventually you get up something like anhydride, which does not have the water molecule in there. So now, interestingly enough, the water molecule plays a big role with regards to your mechanical performance. As you see on the slide, the stress strain slide you will see in there, you will see that the behavior of a gypsum is very different from what you have for the anhydride or even for the hemihydride. So that means the water molecules in between the layers of any kind of minerals, for example, has a huge role to play with regards to that the mechanical performance of the material. Now, obviously, we are doing like very simple tests like, okay, uniaxial tension, shear, compression, and so on and so forth. But you understand the implication of those things when you are talking about something like multi-axial type of loading situations. The one in the part below, which is basically marked as red, you will see that is something called tobermorite. So tobermorite is something like your, actually the gel. We talk about like something like CSA gel, calcium silicate hydrate gel. So that is what is your tobermorite. It's a mineral which is available, and that actually gives you the binding properties to that of the cement. Now, if you look into tobermorite has a lot of different structures: tobermorite 9, tobermorite 11, tobermorite 14, and so on and so forth. All of these, the numbers like 9, 11, 14, they refer to the distance in between the layers. So it is something which is similar to that of the gypsum, meaning that it is also a layered structure, and the distance in between the layers gives you the different names like tobermorite 9, 11, 14, and so on. Tobermorite 9 is something which does not have any water molecules, whereas tobermorite 14 is something which has water molecules. So water molecules actually plays a role and moves the layers apart. And these molecules also play a big role, as you understand that, okay, I mean, this the gluey part of your cement, I mean, the cement mix, that kind of makes up all the adhesive properties and the beautiful properties of that of the concrete. So that is what is being modeled as your tobermorite. So people do work with these type of things. And what we are showing in here is that how that water molecules is playing a role with regards to the mechanical performance of that material as such. Similarly, another example of that is ettringite. Ettringite is, I mean, if you have gone through like cement chemistry or cement cement materials, I believe, you must have heard about the term ettringite. It is also another type of material which is present within the cement when it is being formed or during the hydration process. So we were also working with that ettringite and then seeing as to what is the role of the water molecules, how do the water molecules play eventually a role in the behavior of the structure. So as you can see, what we are doing by all this process is that we are probing the molecular level. We are probing the molecular level as to how that molecular level changes is in fact affecting the structure or affecting the property or the final property of the material. Okay, let's move on. Water. So water, I think everyone has seen water. It is also named as the elixir of life, I should say. But water has very interesting properties. Actually, water is something which makes us all living. I mean, any planet that you are kind of probing out in the space, the first thing that we do is that we check that whether that planet has a water. Planet or star or whatever it is, it has water in that. If it has water, then the question comes, okay, is life in there? That is the next question. Please remember that. If there is no water, then obviously there is no life. So that means water does play an important role. It's a very common material. Everyone has seen water. I think everybody understands that, okay, water much detailed than everyone else, but it's not really true. Think of it like this. Water has an interesting property at 4 degrees centigrade. And due to that property, water, when it freezes, water does not freeze from the bottom up. You will see the water has frozen from the top, but inside a pond or inside a river, the water is still there. So that means the fishes which are present within it, they're still living. So how is that possible? That's the beauty of water. Another interesting property I will tell you about water. Now think about water. When you freeze the material, any material you take, okay, you freeze the material. What happens? The volume compresses. If you want to kind of describe it in one way, you can think of that, okay, I have the molecules, and when I apply some kind of like temperature, cold temperature to it, well, the molecules kind of come compress together, they come closer to each other, and eventually there is a volume compression in the material. So that means if you look into a liquid and that is a solid, the solid will be having much more compact volume compared to that of the liquid, right? Interestingly enough, water is an exception to that entire behavior. If you take a glass filled with water, just plain water, I'm talking about liquid water, you freeze it, put it in the refrigerator, you will see that the volume has increased. Now that's interesting. So water is the only material which is present in Earth, at least what is found in Earth, in which you will see that there is a volume increase on on cooling, or so you understand water is not that simple as what you can think about, even though it is like very, commonly available. Now, what we were probing in this one is a little bit different. As you can see, what I have shown in here is called a phase transition diagram. Phase transition diagram means the temperatures and the pressure ranges at which your water water exists in different formats, as you know, that it can exist as a liquid, it can exist as an ice, it can exist as a vapor, and so on and so forth. So in here, it is showing that, okay, various temperature and pressure ranges at which this one will exist. If you notice very carefully in here, you will see something like 0 degrees centigrade. You will see like different bars, like 1 bar corresponds to 1 atmospheric pressure. And you will see, okay, temperatures and so on and so forth. So depending upon pressure and temperature, the water kind of changes different phases. The ice that you see normally is something like this. It is called 1C or 1H type of ice. That is what you get from the refrigerator. What we were probing is something like this ice 7. If you see a little bit above the liquid, you will see there is something like 7 marked in Roman numerals. So that is the ice that we were probing. There is something which is very interesting about that ice. That ice 7 is actually one of the most densest form of water. You might have already observed that if you take an ice, normal ice which you get from the refrigerator, and put it in the water, liquid water I'm talking about, you will see the ice will kind of float. So that means the density of the ice is much more lower than the density of the liquid water. The ice that we are talking about is ice 1H. But in the case of ice 7, the density is far, far greater than that of the water. So that means if you somewhere or other get to that thing about like ice 7, or if you can manufacture, let's say, for example, ice 7, then that will kind of like sink rather than float on the top of the water, liquid water. By the way, the question is, are we really concerned about this ice 7? What does that ice 7 really mean? I have not seen ice 7 normally. Yes, true. Ice 7, you cannot just get it at a normal situation, because think about the pressure ranges that we're talking about. We're talking about something in the range of like 1 megabar pressure, 100 kilobar pressure. So that's a huge amount of pressure. But ice 7 does remain. Ice 7 you can obtain if you perform some kind of like shock experiments. So let's say you do something like a shock experiment in the water, or liquid water I'm talking about, you eventually end up getting like ice 7. People have reported those kind of things before. Okay, so that's what we were probing in here from a molecular perspective as to how does this ice 7 really form. Okay, we obviously done some kind of like spectroscopy measurements, we did some like radial distribution measurements and many different things. We obviously compared our things with that of the various previous experimental investigations that has been performed. As you can see in here, you will see a lot of experiments being performed, and it says something about like this work is which is our work, which we have done. So in those cases, we basically demonstrated as to how your liquid water is transforming into that of your ice 7. Excuse me. Let me give me some time to drink water. Okay. Now, one interesting thing should come to your mind when we're talking about any kind of like solid. A solid is something which is a crystalline structure. Crystallinity means a structure which has some kind of like periodicity. And this periodicity is there in ice, but there is no periodicity in the case of liquid water. So the underlying question that we were trying to probe is that how does this water, or the liquid water I'm talking about, gains some kind of like periodicity? And this is what we have been doing in here, and we have basically shown that there is something like known as hydrogen bonding, and that hydrogen bonding plays a big role in moving from that of the liquid water to that of the ice 7. Okay, in here, what you're seeing is that I have talked about many different things so far. I've talked about polymers. So polymers are a class of materials in which you see different types of behavior. Polymers usually exhibit something like a chain type of structure. Then I've talked about minerals. Most of the minerals are something like ceramic structures. So ceramic means it has like combination of ionic bonding as well as covalent bonding. It has a combination of both in one way. And so after that, I've talked about like water, which is a very common material out there. So those are all complex materials, I should say. If you talk about something like metals, so metals are not that complex with regards to the molecular structure as such, because metals you do not have like number of different elements within the metal. Like in this case, we are just probing copper. Copper is a very commonly utilized materials for your shock type of simulations, or the shock type of experiments. People always utilize copper for these kind of things because copper has certain characteristics. Now, when you look into these are basically like metallic structures. In these metallic structures, when you subject it to like shock loading, you'll eventually see that there are a lot of different patterns which are getting formed. And these patterns eventually result in some kind of like slip along those planes. You see the small dotted lines, those are basically called the dislocation lines. These dislocations eventually gives result to your slip. And as a matter of fact, this slip eventually accounts for something which you might have known later on, or will be knowing later on, something called plasticity in that of the materials. So if you look into the theory for plasticity, it is basically something, at least for the case of metals, it is basically something like formation of dislocations, slips, twines, and so on and so forth. In the case of copper, there are obviously different types of metals out there. Copper is a type which comes under by the name of face-centered cubic material, or FCC type of material. In those FCC materials, your dislocations and slips play a big role, and the material, after a certain amount of loading or certain amount of stress, it kind of starts moving as a fluid, and that's how you get the plasticity kind of formation. So we were looking into as to under extreme conditions, meaning at extreme loading conditions, like when you're subjecting the copper particle for that of the shock loading, how do those microstructure evolves, or how do those these dislocations or the slips eventually form? Please understand, any material will be having distinctive slip planes. So it is not like completely arbitrary as to where which direction the material will start moving. It has definitive planes and to move along those definitive planes. You can eventually actually say, okay, it will move along this particular plane. So that's what you study about dislocations, and that's what we're doing in here. And dislocations, you have like a lot of different things in there. This is actually a topic which is taught within the materials community, at least who are doing like metallurgical engineering and other things. They at least know something about dislocations, I believe. Okay, so we were seeing different types of dislocations, how do they form, formation of twins, and many other different things in this case. Eventually, all of these things gives rise to something called as plasticity within the material in this case. Okay, copper. Copper not only undergoes plasticity, but also it undergoes phase transformation. Now, when we talked about, or the examples that I gave for the phase transformation is that we are only talking about like moving from the, let's say, the solid to the liquid stage. But it did not be so. It did not be that always it has to, when change in phase should mean always moving from like solid to liquid or liquid to gas and so on and so forth. It can also mean that the crystal structure moves, and there is a solid to solid phase transformation. So the crystal structure moves from the solid state, a solid crystal structure to that another solid crystal structure. In this case, what is happening is you have a copper, which is basically as an FCC, as I mentioned, face-centered cubic, and it under a certain amount of stress conditions or under a certain amount of loading conditions, it eventually transforms into something like body-centered cubic or BCC. So we were probing as to how or where does this move from, how does it move from the FCC stage to the BCC stage? Now, when you do those kind of things, obviously you have to do something called X-ray diffraction. X-ray diffraction is also a very common methodology. It is, numeric. We have done it numerically, but you also can do it experimentally. We have obviously validated our work with the experimental investigations. And when you do this XRD, what you basically probe is what are the different types of lines. What are the different types of planes along which the light will reflect back. Based on those, you can find out, okay, the molecule kind of, or the material kind of exists in this particular orientation, or this has a particular space group. Now, what we were seeing in here is that, interestingly enough, this is actually a first find, we should say, in which we observed that copper under very high intensity shock loading undergoes a solid-solid phase transformation. This was actually the first work in which we predicted that, okay, this is going to happen. We initially did it with some molecular simulations, and then in order to kind of verify that, we also did some kind of like electronic contribution. And quite recently, we have published this one work sometimes back in 2017, 19, around that. This year, I saw that there was one publication which did the experimental investigation, and they pointed out, yes, it does happen. So please understand that computational work does not have to be always following that of the experiment. It can also give you some kind of like indication which people in the experiment can do later on. And that's what happened in this case. The guys who did it at Washington State University, they eventually proclaimed that, yes, this type of transformation to that the BCC structure or body-centered cubic structure does happen when you subject to shock loading. So that was a nice thing. Okay, if you have, any material that you do, obviously it will have some kind of defects. So that's a nature for any material, I should say. Defects can be of many different types. Okay, one of the easiest way of kind of accounting for defect is kind of thinking about putting in voids in the material. Now you can have different types of voids. You can have like connected voids, you can have like disconnected voids, and so on and so forth. So if you put in a series of voids and then you subject it to like shock loading, what are the different types of things that you observed? As you can see, there are something like red regions. So these red regions are basically hot zones. So the temperature in those regions goes significantly higher. So if you can tailor, if you can tailor the material by putting in some kind of like voids and then improve its properties, then that's a nice thing to do. So that's what we have shown in here, that, okay, if you put in a void, then obviously that will change certain shock characteristics. Obviously, we have done it from the point of view of shock, but it can be done for otherwise. Nowadays, people are putting in simulated voids in order to change the material characteristics, meaning, let's say, the plasticity behavior of the material, for example. Okay, so those things are possible. Okay, when we talk about metals, as I say, there are different types of metals. The class of metals, if you want to classify it, it is something like, as I said, one of them is being copper. Copper has something like a face-centered cubic structure. And then there is other types of metals called HCP, or HCP structures are also available. Hexagonal close packed, it is referred to as. So this hexagonal close packed, if you look into the periodic table, I believe all of you have at least at one point of time looked into the periodic table. And periodic table presents very interesting things, I should say. Even though I'm a civil engineer, but obviously I think the civil engineering, if you're obviously interested in like structures, also many other different disciplines, like let's say environment or even the geotech, then you also have to think about the chemistry associated with it. So my work, what I have been trying to do is that to, imbibe in chemistry, physics within the concept of engineering. So that's what research is all about, what I think. Anyway, so if you look into the periodic table, you will see different types of elements, and different types of elements will be having different types of initial structures. If you look into for the case of titanium, you will see that this titanium has something called an HCP structure. HCP means hexagonal close packed. So this HCP structure is kind of interesting, because HCP structure does not give you really dislocations which are essential for formation of plasticity. What HCP structure gives you is something like called twines. So twining is prevalent in case of HCP type of materials. So we have done a lot of different simulations for the HCP materials. This is an HCP. HCP structure is something like this, as you see on the extreme right-hand side. So these are your molecular arrangements. So you have in the top, you have this 1, 2, 3, 4, 5, 6. So 6, and then one at the center of it. And then the middle, you have like a triangular type of thing. And then below, you have something like this. So that's one molecule, or one crystal structure for the titanium. Okay. So if you subject it to different types of loading conditions, we did like compression loading, tensile loading, and so on and so forth, you can activate different types of twining mechanisms. And the point of saying all these twining mechanisms and so on and so forth is basically looking into the theory behind plasticity. How do those plasticity really evolve? Okay. How do those plasticity, which directions of which planar directions the plasticity is going to move? So plasticity is eventually meaning the flow of the material. So the flow of the material, which direction it will move. So that is being given by your twinings. And as you can see in here, if you apply a compression loading, you have like compressive twines, you have tensile loading, you have tensile twines, and many different types of things that can come out of this ones. Okay. Okay. Now, just to refresh some of your memory, maybe some of you at least have seen this one. When you talk about bonding in materials, remember, we have talked about metals, we have talked about minerals, we have talked about polymers. In all of them, at the end of the day, there is something like a bonding in between the atoms, right? So when you look into the bonding, there are different types of bonding which are available. You must have read this one sometimes back in your class 10, 12, I believe. So you have something called an ionic bonding. What does an ionic bonding do? It is basically takes in a valence electron and then gives it from one electron. It gives this Na atom kind of gives it to the Cl atom, and that's how both of them are kind of like valid. So this ionic bonding is quite strong in that regard. If you think of metallic bonding, it is something like these metal ions are distributed in a sea of electrons. So something like that. Everyone has a shared type of thing, and everyone is kind of like floating within it. So that's your metallic bonding. If you look into covalent bonding, it does not give off electrons from one shell to the other shell. They kind of like mutually share the electrons. So that's what your covalent bonding is. Example of that type of material means, let's say, silicon carbide, for example. Example of an ionic bonding is something like sodium chloride, for example. If you have, for the case of metallic, I talked about like copper, titanium. So those are your metallic bonding. Apart from that, you have, remember, any material that you have, it will not be a purely covalent or a purely ionic. It is usually a combination of the two things. So that's how you must have read about something called Pauling's expression, Pauling's expression kind of gives you the bond ionicity fraction. And these things are kind of important to understand. Why? Because you're eventually kind of dealing with the material at least the molecular level or the electronic level. You need to understand as to when this bond kind of changes. The bonding change, let's say the bond changes from the covalent to the ionic or vice versa, then obviously there is a change in the behavior of the material. Okay. So, I mean, just to give an extreme example for that matter, I mean, you can have something like a conducting material, electrical conductor material, that can change to that of an insulator material under certain kind of stress, meaning certain kind of pressure and temperature. Okay. You can develop something like, you must have heard about, at least in your newspapers, you must have read about something like superconductivity. Okay. So these superconductivity materials can be generated under certain conditions. And all of these things, the new type of properties that are coming out in the materials, those can be done by changing this bonding. You obviously do not want to kind of break the bond. I mean, if you break the bond, then, okay, the material, the molecule is kind of broken in one way. But you can do some kind of changes such that this bonding kind of changes, and this bonding change will give you very interesting properties which are unheard of nowadays, or you can think of it in a different manner. Anyway, so that means you have to at least have an understanding of different types of bonds which are present within the material. Now, what we did in here is that we talked about, I talked about different types of metals, right? I talked about like copper, titanium, and all those kind of things, but not all of them are metals. Let's say, for example, silicon. Silicon is a very common material that is utilized for the semiconductor industry. Any computational thing that you have, any mobile phones, whatever you have, right? Any electronic items that you have, it does have silicon in there. Silicon actually forms the basis for all the electronic industry. So that's why you might have heard at least some by the name of like Silicon Valley, right? Silicon Valley is someplace in your California area. So Silicon Valley, why does the name Silicon Valley come in? Because silicon plays a big role. Without silicon, you do not have an electronic material. So you need to understand as to how the silicon material will behave under different types of conditions. As you can see in here, silicon exists in different types of solid phases. As you can see, the normal behavior of silicon is something like a cubic diamond. So the distance in between these atoms is something in the range of like 5.43 angstrom. If you subject it to some kind of pressure, it changes. It changes into something called a tetragonal structure, beta-team tetragonal structure. Some other pressure, it becomes something like orthorhombic type of structure. And similarly, it undergoes different types of phase change. All of them are, remember, all of them are like solids. But even though it is a solid, each characteristic, like let's say the cubic diamond to that of a orthorhombic, different types of crystal structures, they have different types of properties. So any crystal structure, if you can change the crystal structure, even the solid form, forget about like changing it from the solid to the liquid, the property of that material will change. Okay, that's a basic thing for any material. So if you can do that by application of pressure, you can do that by application of temperature, you can do that by a combination of both of them, whatever it is. But if you can change the crystal structure and keep that structure to be like not metastable, but stable enough, then obviously you can change the material properties of that particular structure. So that's what we were kind of like probing in here. We were just applying pressure, and then we are doing the XRD studies in order to show that, you know what, you are getting this kind of structures, and from those structures mean that, okay, you have like different types of material properties which are available. Okay, now I have talked about different types of scales of your simulations. The first, I started off with something like your macro scale to some extent, okay, something like a beam column joint. And then I moved on to something like continuum type of simulations, like finite element simulations, something like that. And after that, I kind of moved into something like molecular simulations. Now, the question is, there is obviously a difference. I also showed you that there is a difference in the length and the time scale associated with different types of these simulations. But at the end of the day, what you have to do is you have to kind of bridge all the different scales. You have to bridge the scales in which you can, do the simulations from that of the molecular or even the electronic level up to that of the like a continuum level. So then only you can really model the things. So that's a big challenge, because bridging in between scales is not a very easy thing. And when we're talking about bridging, we are bridging in two different domains. We are bridging in the spatial scale, where spatial scale means the length scale, and we are also bridging in the temporal scale, meaning the time scale. So let's see. One of those things that we have done is we did something similar in which actually we bridge the things for that of the spatial scale, is that we kind of thought about cement, for example, right? Cement, when it undergoes hydration. So cement, you all know, you take Orland OPC cement, and then you mix it with water, and then eventually you get like a gluey type of thing, which is nothing but calcium silicate hydrate. Now, if you look into the scanning electron microscope of the structure and so on and so forth, you get a lot of different things. You get, as I mentioned before, you get like tobermorite, ettringite, gypsum, and a lot of different things are in there. Okay. So what we did in that case, in order to bridge the scale, is that we took like all of these materials, within your cement paste. Obviously, we performed an XRD and then found out as to what are the related percentages of those materials. And then we kind of like did a molecular simulation in order to find the elastic constant for each of those materials. And after that, what we did is that we did a mixing type of theory we applied, which is called Mori-Tanaka theory in this case. So we applied a Mori-Tanaka theory in order to find out the elastic constant for, let's say, the cement. And we performed ultrasonic investigations in order to perform the cement experimentally, ultrasonic investigation in order to calculate the elastic constant experimentally. And then we matched that, okay, the elastic constant that we're observing from the experiment matches with that elastic constant that we're observing from our simulations. Okay, so that's by this mixture theory, we are kind of like linking up scales from way to that of the molecular level up to that of the continuum level. Now, obviously, this length scale bridging is kind of, it can be done by these kind of mixture theories. But when you're talking about temporal scale bridging, that's a much more difficult challenge. People are still working on that. People talk about something like rare event simulations. Okay, I have also done a little bit of work on that, but that's purely nominal at this point, I should say. We are kind of working on that such that in order to move, okay, I will do molecular simulations, something in the range of like femtoseconds and so on and so forth, but I'll be able to predict as to what is happening at your continuum level, like let's say second stage, seconds or minutes or hours. At those ranges, I can predict as to what is happening to the material. Okay. Anyway, so yes, here you see that, okay, this is how your XRD kind of looks like. You have like different peaks, and these different peaks correspond to different things. In this case, you'll see for the case of cement or constituents for the cement paste, you have like all of different phases. You can see like 16 different phases are in there. This is what is there in the powdered cement. So powdered cement will be having like halite, belite, aluminite, ferrite. All of them have like obviously different types of chemical formulas. What I showed you, C3A, that is basically aluminate. Okay. And gypsum I also showed you. I also showed you something about ettringite. I showed you something about tobermorite, and so on and so forth. You see the different type of structures that are in there. So these are what is present within the powdered cement. As you kind of like put in water, eventually you kind of get like different types of compounds in here. And after 28 days, as what we know as the hydrated cement hydrated cement paste, we get different types of compositions. These are different weight percentages. So we take all these weight percentages and then put it up in our chart. Eventually, what we get is that, then we perform that, okay, elastic constants for all of them, all of these individual things. And eventually we come up with a value of your elastic constant with something like 30.3 gigapascals. And if you do ultrasonic type of test, which is basically an experimental investigation in order to find out the elastic modulus, that's what is done for any material for that matter. So if you do that, you get something like 28 GPa. So I think we can safely say that the methodology that we are prescribing is quite matching with that what you're obtaining from that experiment. Okay, now, as you might have noted, when we talk about these extreme loading conditions, many of these materials are of interest either for the defense or for the space So we have done, I mean, I primarily work with the defense region. I mean, space, I have worked once, and I will be working in the future, I believe. But most of them, it is basically defense type of applications. So there are a lot of different applications. Some things are copyrighted information, so I cannot show that to you. For example, like I work with also like different types of explosives materials like RDX, TNT, and so on and so forth. But those things I will not be discussing in here. Those are of relevance to any country that we are talking about, right? So obviously that is not an open discussion. So I'll be talking about some materials of interest which are of the defense, which are at least which is also of interest to that of any civilian for that matter. So one of those materials is basically a sandwich composite material. So sandwich composite, we do have a lab setup in which we can manufacture sandwich composites and different types of sandwich composites for that matter. The project that I kind of like highlighted in the blue is that, I mean, it was basically funded by the Navy. So the Navy was kind of interested in these type of materials in which it has a PVC foam and the glass fiber and epoxy resin. But there can be also other different types of materials which we can do. Like, let's say if it is an aerospace application, then the primary thing which I'll be working on is basically metallic foams. Okay, so metallic foams, you'll have metallic foams. Usually they're like titanium foams are available, or aluminum foams are available, and then titanium foils are available. So you can mix the two things up together in order to, if you're working with something like aerospace industry. Anyway, the main point is that we are basically making sandwich composite materials, and in sandwich composite materials, there is a different types of technologies that are involved. This methodology that we are talking about in here is called VARTIAM, or vacuum assisted resin transfer molding. There are also other types of methodologies like autoclave, and many other different methodologies are available. These materials are utilized for, as you can see, the ships in here. So let's say if you're talking about the US Navy, you have Zumwalt DDG 1000 destroyer. I mean, the size of the ship we are talking is quite big. I mean, it can accommodate like a couple of football fields, I should say. Okay. Yeah, I mean, it's in the range of like hundreds of meters I'm talking about. These materials are utilized for the hull structure of this type of ships. It is also utilized for the Swedish Navy Landsort type vehicles. It is also utilized for Avenger class vehicles. Now, you might be thinking, okay, why are we really using these structures? Think of it like this. It has a core structure. Core means it is like a foam type of structure. So when you apply a real load to it, this foam will kind of compress, and it will allow the compression thing in there. So that means these materials are good if there is a blast or anything like that. So if you have a blast, then this material can compress and you can take up the load without the material kind of like tearing up. On the other hand, these materials can also take up the strength, which is similar to that of the steel. So previously we utilized steel, but nowadays we do not utilize steel. We utilize this type of materials in order to build our main ships, naval ships I'm talking about. Okay. So, okay. So what we have done with these kind of things is that one of the major problems whenever we are talking about like sandwich composites is delamination. Okay, you understand that there are like two different materials in there, right? One of them is the face sheet, which is a glass fiber type of material typically, and other of them is like a PVC or foam type of material. So they are like distinctive characteristics, and they are kind of like glued together by means something like an epoxy resin. So obviously the weak point on the material is the interface region, and that interface region is prone to cracking and kind of delaminating. So that's quite a common thing. So we devised some kind of like methodologies by which we can prevent this delamination. One of them is something like called a shear key. It is something like a ridges that you placed within the foam, such that even if there is a crack which you can initiate, that crack path will kind of get deviated, right? So that's a application of a shear key. And then also we can do something with like carbon nanotubes. If you put like carbon nanotubes, then those carbon nanotubes forms like some kind of like chains, and that kind of prevents the crack from forming. So these are two different methodologies by which you can kind of, I mean, at least what we have worked on. There are obviously other methodologies, one of them being stitching. We have not worked on that. So by these two methodologies, we can prevent delamination. And we have done numerous different tests with various different things. Like we have performed like mode 1 type of simulation, mode 1 type of experimental investigation, mixed mode type of simulations in which you can have a fracture propagating both under normal and that of the shear loading, okay, and so on and so forth. We also, this capturing of the delamination is also very interesting, because usually you cannot see the delamination from the face of it, because it is something which is happening inside your body or inside this material body. So capturing delamination is also very troublesome matter. So what we did in that case is that we put in different types of optical fibers. Optical fibers, the diameter of the optical fibers is something which is like very smaller than they are here. So you understand that it is like very small things that you're putting in inside or embedding it within it. And then you're kind of like passing light, and as you're kind of applying load to it, the frequency of the light kind of changes, or there's a change in the frequency of the light that is being transmitted. And with the change in light frequency, you can find out, okay, what is the strain that is being developed in the material. So that's what we are doing in here. We developed two different types of methodologies, and actually this one was a project which was funded by the space agency ISRO. So in this, this one was primarily meant for like, okay, you have like sandwich composites for rockets and other things. So how would you find out in situ, like, okay, while the rocket is kind of going up, let's say, for example, how do you find out that whether there is some material, some region which is like weak, or there is some kind of delamination? So for that, we kind of generated something like, okay, we put in these optical fibers, and then we can do a real-time monitoring. Okay, what is really happening at the interface level in between your glass fiber and that of your PVC, for example. Okay. We also did carry out some kind of like underwater explosion test. This is at a facility at Visakhapatnam in NSTL. It's Naval Science and Technology Laboratory in Visakhapatnam. So we kind of teamed up with them. We made like these big sandwich panels, okay, like glass fiber and then PVC foam. And then we put it underwater, because our application was basically, as I said, Navy, submarine, those kind of applications. So we'll put it underwater. And then as you see in here, there's a small explosive, plastic explosive. So this is a very small charge, like not even 5 grams, and 5 grams of TNT, basically. So we put it underneath the structure, something like this, and then you let it explode underwater. So as you let it explode, you see as to what are the kind of dimples that are being formed in this case, and then compare that with that of the steel. I mean, if you have a similar weight of that of the steel, then what would you do with that? Obviously, what we found out is that obviously this material performs much better than that of the steel. So steel is, first of all, much heavy. So if you are increasing the heavy of, the material is being heavy in itself, so that means it has, it is not lightweight, and it cannot carry that much amount of passengers, for example, or other equipments in there, right? So if you have a material which is like lightweight, so that is kind of good for the Navy. So that is why this material is kind of utilized by the Navy nowadays for any kind of naval applications, at least. Okay. Now, I mentioned previously, all of those cases that I've described so far is primarily related to that of mechanical type of situations, meaning that we apply some kind of mechanical loading, whether be it a projectile impact, whether be it a blast or a shockwave type of situation, or some kind of like natural hazards like earthquake and so on and so forth. And what happens to the material? How can you change the material and so on and so forth? But extreme conditions, when I'm talking about extreme, it is not only always the loading component of it. It is also, it may be that your material may be subjected to some extreme weather conditions, for example, like extreme environment. Think about a ship. I do not know if you have seen, you might have seen a beautiful view of the ships that are nice and clear, but there are different types of sea states that are available. Maybe what you can do after this one is that you can type in something called a sea state 5, okay? Type that one in your YouTube, and you can see as to what that condition means. You'll understand that there are different types of sea states in which your marine structures are subjected to. So obviously, when you're putting up a ship, you have to kind of like get it up such that it can do different types of, or it can withstand different types of marine conditions. And one of them being the extreme condition is like sea state 5. So sea state 5, if you look into it, you will see the amount of waves and so on and so forth. Apart from that, these ships also operate under extreme conditions. Like let's say, for example, if you have a ship in Alaska stationed there for like, I don't know, 2 months, 3 months, temperature in Alaska is usually in the range of like -20 degrees centigrade, roughly. almost all throughout the year, apart from at least 1 or 2 months in which it goes above 0. So in those type of situations, you are actually placing your polymeric material or whatever the material that you're having in there in the ship to those kind of extreme environments for quite a long bit of time. Now, we know for sure that metallic materials do not, there is no kind of like degradation in the metallic materials as such, but obviously they're heavy. But on the other hand, polymeric materials are lightweight, but they do degrade under extreme conditions. So what we were kind of probing in here is that, okay, let's say I have your glass fiber composite, for example, and then I keep that under extreme weather conditions like your -20, -30 for an extended period of time, and then see if there is any kind of degradation in the material. So that's what we were doing in here. Obviously, we were doing a lot of different things like digital scanning calorimetry, your IR spectroscopy, terahertz spectroscopy, and then looking into the molecular aspect of it as to how the molecule is kind of changing. Okay, along with time, once you're subjecting it to like significant amount of, temperature conditions. Like in this case, we were kind of proving it under on a -20 and -80 degrees centigrade for a long period of time. I'm talking about like 2 months, 3 months around that time. In here, actually, what we did is that we actually were probing the epoxy resin because, as you know, the epoxy resin or any resin for that matter is actually the one which kind of holds the things together. So if that material kind of degrades, then the other materials will obviously degrade, and there is no point of there is no holding in between the materials, right? So that is one of the crucial things that one needs to understand. So in here we were talking about like very cold temperatures. In here we were talking about, let's say, saline environment. What happens in a saline environment? The sea state is obviously not like fresh water, right? It is eventually like saline water. So saline water does have an impact to play. It does corrodes. It does many different things. So we were looking into that. By the way, we have a terahertz spectroscopy. I will not deal with that because we kind of set it up. Actually, this is not something which you get in the commercial market. You eventually have to set it up yourself. So eventually we have that, and there are a lot of obviously physics and other things associated with it. We did it in collaboration with one of our physics department professors. I'll show you as to how I talked about earlier. I said there's something like IR and IR spectroscopy and terahertz spectroscopy. IR, I said, is that something which probes the vibration of the bond. Like let's say if you have a CH bond, you are probing the vibration of the bond. In the case of terahertz spectroscopy, you generally do not probe the vibration of the bond. You generally probe the vibration of the entire molecule. Okay, so there is a distinction between terahertz spectroscopy and IR spectroscopy. So we have done it with experimental as well as numerical simulations, and this is one video perhaps you might want to see as to what do you mean by molecular vibration. The molecule that you're seeing in here is DGEBA. DGEBA is a complex molecule, and that is one of the constituents for your epoxy resin. So if I look into the molecular vibration, it is something like this. So one of the vibrations, or one of these peaks corresponds to a motion which looks something like this. So your entire molecule kind of vibrates, and you can pick up that vibration and then say that, okay, you can say something about that molecule. Okay, you can probe it. Obviously, we are doing something like a simulation at a electronic level in order to do the simulations. And when you're doing the experiments, you are doing basically terahertz spectroscopy. Okay, so I have talked about many different things, primarily for the material, not much for the structure, apart from the fact that once I described about the beam column joint. Okay. By the way, what am I doing with regards to the time, Shubhajit?
Because it's the evening time, so everybody can basically provide that time. You can continue.
Okay. So continuum studies which are of interest. Now, I will not go through all the equations as such. Okay, that is not the objective. Equations, but one thing you have to understand that whenever you're doing, so please don't look into the equation. Just look into 3 different things written there. You have a mass, momentum, and energy. Okay, so these things at least you see. Forget about the equations. So what you do with that is that any continuum simulation that you do, you have to kind of conserve these quantities. That's That's actually a requirement for any continuum mechanics simulations that you do. Okay, so you have to conserve the mass, you have to conserve the momentum, and you have to conserve the energy. And that is done in any conventional continuum mechanics problems. Now, when we do shock waves is something which is interesting, because the shock wave is something you have a discontinuity in the pressure field, you have discontinuity in the displacement field, and many different things. So when you talk about like shock waves, there is nothing. There is if you look into an integral or differential equation, those type of equations you will not get. You'll get like discrete equations, and those discrete equations for the conservation of mass, momentum, and energy, they refer to as Rankine-Hugoniot jump conditions. So that is what I've kind of explained in here. You have an incident shock, and then it kind of gets reflected from one particular surface, and it becomes a reflected shock. So what you need to do, and so on and so forth. So at least you need to satisfy the three conditions, and then obviously put in some kind of material model. In this case, you are putting an equation of state. So in this, we generally do it like Mie-Gruneisen equation. There are other equation of states which are available. So you put in some kind of like equation of state, and eventually you put in an initial pressure, you get an output pressure, and so on and so forth. This is a standard gas dynamics type of simulations that you do. So interesting thing is, now the question that we were probing in here is that, you know what, shock wave can, forget about the equations, as I said. There are a lot of equations, and yes, once you're interested, really interested in the topic, then maybe you can go to the equations and then understand in much more detail. But the outline of it is something like this. Let's say you have a shock wave which is passing through the air, right? You must have always, at least all of you have read about ideal gas equation of state, right? What does this ideal gas equation of state do? If you remember from your class 10 to 12, you will remember that, okay, PV is equal to nRT. That's your basic equation for the ideal gas. Ideal gas, what it does, that it relates the pressure, the volume, and the temperature by some way, some equation. So PV is equal to nRT. When you're doing that, you are basically relating the pressure, volume, and temperature. Together, you bring the three things together. That's your equation of state. So what you're meaning by that, you change the volume or you change the temperature, you get some different pressure. You change, either of the two you change, or either the one of you change, one of them you change, you get the variation in the two different things. So that's a relationship you build along with that. Now, you must also note this ideal gas equation of state is not something which is applicable under all conditions. Like, let's say if I'm talking about like shock waves and other things, we talk about like generally huge amount of pressures. We talk about like huge amount of temperatures. In those cases, your ideal gas equation of state is not valid, actually. So researchers, what they have done is that they usually take this ideal gas equation of state, and then from there they talk about something like CR. CR means basically the ratio of your reflected pressure to that of the incident pressure. Okay. So in the shock wave, this is one term which is referred to as CR, reflected pressure by the incident pressure, and they have predicted that, you know what, from simulation, there's actually an MIT group which actually did this work. So they took the ideal gas equation of state, and they say that, okay, your CR cannot be more than that of, let's say, in this case, 8 or something like that, 7 or 8. Now, after reading to that, we understood that, okay, maybe the ideal gas equation of state, what they're talking about is not, because they kind of missed that point, thinking about that ideal gas equation of state is applicable at those pressure and temperature ranges. So what we did is that we changed that ideal gas equation of state and put in some other equation of state. In this case, we were putting in another equation of state, which is basically your van der Waals equation of state. It's a real gas van der Waals equation of state. So when we do that real gas van der Waals equation of state, we can see that your CR can eventually go up to like a value like 20 or so. Something which has been mentioned previously in literature in 1940s when they were doing this Manhattan Project and other things. They mentioned that, okay, the value of CR can go up to the ranges like 20 or so. But that was not being predicted from theoretical observations. What we did is that if you change the equation of state and put in a proper equation of state, yes, you can show that it can go up to 20. So that was a very interesting observation. And that, okay, you might be thinking, okay, why do I really need to care about the shock waves through the air? Well, first of all, if you think about an explosive, it first of all bursts. And then there is a transmission through that of the wave, transmission wave through that of the air, and after the air comes the structure. So once you understand as to how the shock wave is kind of propagating within the air medium, then only you can find out as to what is the impulse that is being transmitted from the air or from the shock wave in the air to the other structure. So you have to understand this philosophy behind, I mean, this understanding you have developed. So that is why we kind of did this work. We did it for the air, and also we obviously did it for the water, because water is the concern, at least in our navels area. In the case of water, it's much more actually complicated. You just do not have just a shock wave which is kind of hitting the structure. Let's say if you have a bust in here, as you can see, my pointer is, you can see there is something written as bust. So if you have a bust, you will see, or basically this is an explosion in there. You will see that there is something like a cavitation type of thing which occurs. Okay, and then at the end of the day, you will see, obviously there is a shock wave which kind of travels, no doubt about it. And then at the end of the day, you will not see any of this cavitation or the shock wave in there. What you will see is the huge plume of air, water. And that is actually the breaking of the cavitation wave at the surface of it. So there are a lot of things which are involved, a lot of physics which are involved in an underwater explosion process compared to that of an air explosion process. Underwater explosion process involves not only shock wave, but also cavitation dynamics, cavitation bubble dynamics. We mainly concentrate on the shock wave part. Cavitation bubble dynamics is actually what we are doing with one of my previous students. So we have a work, we have proposed a work, and we eventually were working on that, like towards cavitation bubble dynamics. But the work that has been already completed is basically of the shock waves, as to how the shock waves kind of pass through that of the air. Air we have already demonstrated. Water is what we're showing in here. Okay, so we have a lot of different things. We have as that of the air, we are showing that how the CR kind of value changes along with the different pressures. We have also shown that, okay, if you have a rigid surface, how that surface is going to behave, or how that there is a fluid structure interaction which kind of happens, right? So there is a fluid. If you think of the water, and the structure, which is basically something like a rigid structure, you can also think of that as a deformable structure. You can also think of different ways in that structure. So there is a fluid structure thing which is involved, and how that the fluid structure eventually involves your simulation. Please understand that these are basically coupled problems. You just cannot say that, okay, I want to deal only with the structure, I want to deal only with the fluid. If you are interested in finding out as to how or what is the amount of pressure that is being transmitted to your structure, you have to do a proper fluid structure investigation. And that fluid structure investigation is what we are doing in here. IP and II is basically the impulse which is transmitted. Okay, so we were kind of doing it with different types of existing theories, one by Taylor, other by Liu and Yang, and showing as to how our model or our prediction of the theoretical prediction is kind of better than theirs. Obviously, as you might have seen, that we talked about sandwich composite, because that is the type of material that we use for our naval kind of scenario. So obviously those materials will be having some kind of voids, and when you're kind of putting a pressure to that, those voids will kind of compress, and that will kind of influence the structure behavior. So that's what we were looking into also. Along with that, we are kind of like bringing this core compression model. The core will kind of compress, and if it compresses, then what happens? So that's what we are bringing in. The shock wave that you have on the structure, it may not be entirely a normal shock wave. Normal shock wave means the incidence. Think of it like this. So you have a rigid structure, and the shock wave which is kind of hitting the structure is at 90 degrees to that of the structure. It may not be like that. It may be something at an inclined angle, right? So what happens if you have an inclined angle? So those things we were kind of like doing with different types of shock pullers. These are referred to as shock pullers. And we were seeing that, okay, how do the shock pullers change in the case of water? This is actually a new work from us. There is actually no work in the shock puller in underwater situation. There are a lot of work for shock pullers in the air domain, but not in the underwater domain. Air domain, they are kind of interested because they are also interested in, like, let's say, if you have a plane, let's say, for example, you know that there are many defense planes which goes above Mach 1 speed, or which exceeds the speed of sound. So speed of sound is like Mach 1. So if it exceeds the speed of sound, then it is referred to as more than Mach 1. And in those cases, you have a sonic boom. And in those situations, what happens and so on and so forth. People have done a lot of study on that. But underwater, there is no study. So we were actually one of the first in order to do this kind of studies for shock pullers underwater. And we showed that, yes, there is also generation of Mach stem. As you can see in the small picture down in here, you will see that there is a Mach stem which develops. Now, what is the Mach stem and all those kind of things? If you're interested, maybe you will learn it at one different point of time. Or, I mean, if you even give a search on the internet, you'll find as to what we mean by Mach stem. Please understand, any commercial flight that you have, almost all, I think all of you have taken some kind of like airline travel, almost all the international flights that you have, or international national flights that you have, they travel, these commercial flights travel at a value of like 0.8 or 0.75 Mach. And here we are talking about something in the range of like, let's say 2 Mach, 3 Mach, all those kind of situations. Where these situations are important? Well, think about something like hypersonic type of vehicles, hypersonic or ballistic missiles, for example. So that means, let's say I press in a switch in here from, let's say, New York or Washington and reaches Moscow in like, let's say, 15 minutes. So those type of ballistic type of situations that when you're dealing with, we are talking about hypersonic type of travels. Hypersonic travels means the speed being in the range of like Mach 15, Mach 20, around that range. In fact, that is also the same type of situation which is envisaged when you see the space. I mean, the people who are in the space vehicles, they kind of return back to the Earth. The space vehicle which kind of returns back to the Earth, they cross the Earth's atmosphere at a range of like around Mach 10, Mach 15, around that range. So obviously the materials that they should withstand, the material that should withstand that much amount of pressure or the heat, obviously there is a huge role to be played in there, right? So if I'm talking about those type of situations, this Mach thing becomes important, and Mach stem as to how it is being generated in the case of an oblique impact, those also becomes important, and that's what we have done through our analytical studies. I should kind of, I mean, nearly complete the thing in here. So all of these works that you have seen are obviously being done by my students, most of my PhD students. And some of the PhD students, they have already graduated, they have moved on in their lives. I have a few more PhD students in there at Kharagpur. And all of the agencies that have funded this research are basically various agencies within India and also some agencies in USA. Right now, actually, I'm working with some of those Office of Naval Research type of work at USA. So I do these kind of things typically for materials at extremes. Now, just to do a final slide, I should say that when you deal with like shock waves and other things, it is a never-ending type of research domain that you have. You think about, like, if you're interested at one point of time, the shock wave has applications in many different applications. I was talking about something like this one, aerospace and hypersonics. You have something like space vehicle entry or exit from the atmosphere. You have like these planes which are moving at more than Mach 1 type of speeds. These shock waves are also important if you're talking about like national security. The one picture that you see in here in where the cursor is there is basically an underwater explosion. This one is an explosion of a like similar to that what you have seen in Hiroshima and Nagasaki type of situations, like a bomb. In the case of an asteroid impact, like in astrophysics or geophysics type of applications, you do have some meteors kind of striking the Earth, or asteroids like striking the Earth. It creates a huge, big dimples in the Earth region. There are like a lot of places in the Earth where these things are there. And many people are studying that as to what is, you can think of like, okay, how did the life originate on Earth at the first place? Well, is it due to those meteors which comes in from the outer space? Or is it something which happened inside the Earth? So there are like a lot of interesting studies which kind of goes into the astrophysics and astrochemistry region, which deals with shock waves. If you think about like normal public safety or contact sports, like, okay, falling from a motorcycle or doing a boxing match, well, or a rugby match, for example, or an American football, whatever you want to call it. Yes, there are situations in which you do get like huge amount of shock or impact type of situations. The shock or impact situations are always not bad. Okay, some of them they're also utilized for various medical applications. Like let's say you're doing lithotripsy. Nowadays, lithotripsy is very common. What you do in that is basically you pass in this. This is actually a picture of the lithotripsy. You have something like your stones, which are present within the kidney, and you can kind of break those stones and then take it out. So that the process is known as lithotripsy, and you can do that, and some shockwaves are being utilized for that as well. In nature, obviously, in all of these applications that we see, we have always have to look into the nature. Nature presents a lot of different things which we try to imitate, I should say, but we have not been successful in so and so in getting that completely. Think about a small woodpecker. An woodpecker kind of like bangs his head at least more than 1,000 times. If you calculate what is the acceleration that head is kind of impacting, is something in the range of like 1,000 G. Okay. Now, a human head, you bang it 2 or 3 times, you'll feel dizzy. That much I can assure you. I tried myself. So, woodpecker. The question comes is, okay, how does the woodpecker brain not get affected by so much banging on his head? That's a very interesting question. So maybe we can learn something from there. There is also a thing about a mantis shrimp. Shrimp also is very interesting. It can give you a shock. I mean, I do not know if you have seen a mantis shrimp, or at least try to put a hand in the water which has a mantis shrimp and feel the shock of it. You will you will understand as to what I'm talking about. I mean, do a certain net, YouTube, do a certain mantis shrimp shroud, and you will see as to what it means. So I would like to end saying that, okay, any problem that you look into, you have to understand as to what you're trying to probe. What is the question that you're trying to answer? So any problem, I've shown you a structure this is basically a very plain structure of a beam column joint. So if I were to think about from a continuum perspective and give an understanding to that for a design engineer, okay, how he should build or his structure, well, I'll be obviously doing some kind of like continuum simulations. If I were to say, you know what, I want to kind of take a little bit deeper look and then think about the material, then yes, I can propose in some kind of material which will be resistant to this kind of things, okay, like maybe a fiber reinforced concrete type of situations. If I want to think about like, okay, which fiber is better compared to the other one, then I have to look into much more lower scale at a molecular level. So it depends which problem you're trying to address and what you want to try to address. That's what is important. I guess with this, I will end my presentation. If you have any questions, I'll be happy to answer that.
Thank you. Thank you for your kind presentation. I'm quite impressed that the work you are doing at the Kharagpur as well as in that John Hopkins. I hope our participant get some ideas that the civil is nowadays not only about the structure building.
Yes,
yes. Travel a lot because material part is also very important for our civilization structure, and for the extreme weather condition and extreme environment conditions. We have to, if you want to do the study of the material, basically you have to study the structural behavior of the material itself. So now it's depend upon you up to in which scale you want to do the study, in the continuum scale or in the molecular scale or in measure scale. So I'm quite impressed that the research work is the Professor Mitra has carried out. Now we want to take some questions from the participant. Let us see if there any question or not.
I can switch out the presentation, right?
Yes.
I guess. Just hold on.
You can cancel that sharing. The right side.
Yes, I cancelled it, so it's fine. Yes.
There is one question, sir. You can see that message box which is there upside.
Yes, I can see.
And the last question, Jitu Panda, what is the relation between column and the beam in design side? But it is offbeat little bit from today's topic. What is the relation between column and beam in design side?
I actually did not understand your question, frankly speaking. So basically, what why don't you tell me a little bit more about what do you mean by column and beam in design side?
Yeah, Jitu, can you unmute yourself and ask the question? Is there any question? You can type it here or you can ask. You can unmute yourself and you can ask the question. Okay. Sir, I want to ask in favor of the participants. Suppose the work you are carrying out, if any of these participants want to carry out that type of research in India, then where they can get this type of facility in India, and how they can approach there, the ISC Bangalore or some naval board, or where they can have get this type of facility.
Okay, with regards to like experimental facilities, if you want to look into it, the shock tube facility that you have, it is present in IISc, and from IISc it has been it has actually moved on. I mean, IISc is actually one of the forefathers for the shock studies, and after that it has moved to different IITs as well. Like IIT Bombay has one of them. IIT Bombay Mechanical Engineering has one shock tube. We also at IIT Kharagpur have one in the civil engineering department. And then in IIT Guwahati, we have one in the, I forgot, what is the mechanical or the civil engineering department, either of them it may be. So you have, nowadays you have almost like shock tubes, almost in all places, at least all the IITs, that much I can tell you.
Okay. So
if you want to think about like your Kolsky bar type of situations, Kolsky bar is there at your ISC. It is not at IIT Kharagpur, it is not there. But in IIT Delhi, I think it is there. Other IITs are also picking up. Actually, Kolsky bar, not all of them really work on in that. Actually, the problem, what I see in Indian academia, is that it is very difficult to kind of get these experimental things running, frankly speaking. To procure the experiment, I hope you have also realized that, right? I mean, to procure the experiments and procure these things is very difficult, and there are not like national manufacturers out there, so that becomes really difficult. But if you want to look into the computational side of it, there are many people who does these kind of works. Okay, I think almost, at least what I'm aware of, at least all the IITs, they have at least one or two faculties who are at least working in this area, these areas. That much I'm aware
of. Okay. So we are not getting that interesting questions.
Yeah, I think he mentioned something about like, okay, what is the relation between beam and column in design side about size? Okay, so size, I still did not understand it properly, but what I mean by, I hope if you're looking into any kind of like structure, then you will see the beams are at least in the range of like at least like columns are like one floor, let's say, for example. So one floor is in the range of like around 10 feet, roughly, on the higher side of it, right? So that means, and that the 10 feet thing, you're kind of modeling with only like one element. So that is why what I was trying to say is that you cannot really do a continuum type of simulation, or rather something like a finite element type of simulation for the columns. What you can do is that you can take a line element for the beam and the column. Obviously, you cannot take like just any line element. There are obviously specifics for that. You can, where you kind of incorporate the material parameters and so on and so forth. So if you look into the column, the size of the beam and the column, you're looking into the range of like 1 meter to around like 3 meters, around that.
Okay, we're not getting any other question. Okay, so we have to end up this session. Okay. Thank you very much, Professor Mitra, for your time and the devotion you give for our presentation at our faculty development program. I hope our participant will be are benefited from this type of talk, because they are getting new ideas. Probably they don't have the all facilities, but what sir told, that you can do some sort of numerical analysis, some computational things at your end, and then you can collaborate with the faculty of IIT and IISc, and you can take the experimental facility there. But again, you have to take your initiative first, because all these topics are very new, and very few researchers are working on this topic. So you also can take up this issue. Okay, so at the last, I want to thank again Professor Mitra for your presentations. So we'll conclude the session here. Tomorrow again we'll meet at tomorrow 10 a.m. we'll meet again. Thank you.
Okay, thank you, Shubhajit. See you. Okay, bye.